Okay, so in this example, we're given the change in Gibbs energy for a certain constant pressure process. That's a very important part. Constant pressure process is given, there's this expression for it, and we're asked to calculate delta S for that. Right. Now, we can do it in one of two ways. You can go like really, if you want to call it first principles way, then you could say, well, we know the definition of Gibbs energy is that Gibbs is equal to the enthalpy minus the entropy, or T entropy, and then that means that the derivative of Gibbs is equal to the internal energy. Oh my goodness, sorry. First, I skipped a step there. First is just equal to the internal energy plus PV minus Ts, because that's what the enthalpy is, and then you can take the derivative of all those things, and you can really write out all the mathematics, and then eventually you'll get to a part that says dg is equal to v dp minus s dt. Right, you'll get to something that says that, which is also, but what is that essentially? That is the one of the fundamental equations for, well, the fundamental equation for the Gibbs energy, as we've spoken about in class. So you can actually just start there from the beginning, and you can say, well, we had a constant pressure process. So in other words, we want to say then, well, constant pressure means that the change in pressure is zero. So in other words, we're dealing here just with minus s dt. I can really write that nicer. This is equal to minus s dt. So in other words, if we want to divide that, then we can say that dg over dt is equal to minus s. Right. So that's sort of a very long way to get there. The very easy way is to just quickly say, if you're looking for a way to connect delta S with delta G at constant pressure. So like those are the three things that we're asked. We're given a delta G, we're given Gibbs energy, right? We're asked to calculate S, and then we're given its constant pressure. You just go and look at your Maxwell relations, and you quickly go and scan through them and say, oh, then you actually see there is a Maxwell relation that looks exactly like that. So there's an option where you can derive it. You can always derive it. You don't have to memorize Maxwell relations. You can always derive them from first principles. But they will be available in a table in your at the back of your script on your, what you would call it, formula sheet. So you can just go look them up. You just need to know what to look for. So you're looking at constant pressure. So the P needs to be there at the bottom. And then, of course, you're looking for S on the one side. Okay. So that's what we're basically going to use. So we have a function now, a way now of connecting delta G or G with S. We're given a function of G, but we're not looking for just G and S. We're looking for the changes in them. So that might be the part where it becomes a bit tricky in the sense of just understanding exactly what we're doing. But it shouldn't be, because these are state functions, remember? So what are the properties of state functions? It means that we don't really care what happens in between. We can always work with the initial and the final values. So in other words, if we take this is a combination of state functions. So we say then that the initial Gibbs energy derivative will just be equal to the initial entropy. And similarly, the final Gibbs energy derivative will just be equal to the final entropy. Okay. So that actually just solves all of our problems. Right. Because then we have a value. So what is delta S? Delta S is SF minus SI. And SF in this case, so let's just take away the minus here, make this a bit easier to read. So that is SF, and we have what minus SI is. Minus SI is the positive of that thing. So minus SF is minus dGF over T P, and then it is minus SI is plus dGI over T P. Right. And then actually, if you look at how this is written, here we have technically, we have something that is similar here at the top, so we can take that outside. So we'd have here equals minus, minus d dt. I'm just writing it slightly different to how it's done in the notes, but it's more because I know this is how you see it a bit clearer. So I'm keeping it minus, it's GF and then because we've taken a minus outside, so the minus is now outside the entire bracket, right? So we have a plus here, and we want a minus, and we want a plus. So if we have a minus outside the entire bracket, then we need to remember to make this a minus, right? Because we take that minus back in, it's going to become plus GI, and that minus stays there, so it remains minus GF. Sort of like a single person, it's a minus a GF. Anyway, okay. Then we're left with that, and GF minus GI is what? That is the same as delta G. Okay. So then we can just plug that back in. So we have the partial derivative of some function called delta G P. Okay, so it's actually the partial derivative in the change in Gibbs energy to T at constant pressure, which is exactly what we're given. We're given a function at constant pressure for the change in Gibbs energy, right? And that is equal to the change in entropy. So we just need to plug this person or thing or whatever it is into there. So let me do this on a new line. So in other words, delta S is equal to minus d dt. I'm just going to drop the p for now because it's irrelevant. Then you plug in your delta G function. Right? So what is the derivative of a number? So in other words, this thing becomes 0, right? Because the derivative, there's no t's there. And the derivative of that, right? So there's a number, but it's times t, so that becomes dt dt. So in other words, that just becomes 1. So it 1 times 42.8. So eventually we're left with minus 42.8. We just need to check what the unit was. So in other words, it would be, this unit here at the bottom here was per Kelvin, and delta G is in joule. Oops. So it is in joule per Kelvin. Okay. Which also corresponds to the unit for delta S. All right. So I think the trickiest part actually is just first initially obtaining this Maxwell equation. So just getting used to finding the right Maxwell equations, identifying them correctly, and then perhaps just this rewriting. But I mean, after that, it's just a normal derivative, not a difficult derivative at all. And then lastly, just remembering your unit is very important, because I mean, you've done a lot of math and then all of you just chuck the unit away at the end. Okay, it's a very nice example. I quite like this one. Yeah. Okay, I hope this made a lot of sense.